Hello everyone, this is Arya Peruma with the Coding for Young Minds community organization. I will do a quick virtual testing on an existing 3D model of a bridge using finite element analysis to calculate the maximum resultant deflection. The first step in the simulation process is to complete the material definition. I will choose plain carbon steel from my existing material library. The second step is to define supports for a mathematical model. For this example, I will apply fixed support to both ends of the model. Once the support is applied, you can clearly see the visual feedback indicating the applied boundary condition. I will now apply a uniformly distributed static load of 5,000 pounds on the top surface of the mathematical model. Once the force is applied, you can clearly see the visual feedback indicating the applied boundary condition. Once the load is applied, we will run our analysis to complete the mathematical calculations. Since we are doing a quick deflection study, I will use a default coarse mesh to run our problem. Once the solution is complete, we'll be able to see an animation of induced deformation. The deformation scale factor applied to this model helps us to see the direction of deformation, and we can clearly see the bridge moving correctly under the applied load. We will now plot the resultant deflection for the bridge. The maximum resultant deflection on the bridge is around 1.96 millimeters under the uniformly applied static load of 5,000 pounds. The next step is to modify our bridge geometry in order to improve the load-bearing capacity. We can now study how the deflection changes when we modify the geometry. I will increase the thickness of the top plate of the bridge to 1/2 inch, which is 0.5 inches. I will rotate my model, and we can clearly see the existing channels that are used to stiffen the top plate of the bridge. I will increase the number of channels to 13 to provide additional support, and in essence, we are increasing the section modulus of the overall cross-section to increase bending resistance. To achieve this, I will change my spacing for the existing linear pattern and at the same time increase the number of channels in both directions. Now we are ready to run mathematical calculations on our newly modified bridge. And at this point, I will rerun my analysis to complete the mathematical calculations for the modified design. Please note that we do not change our load value or material definition. We are now able to see the new deformation plot to verify that the bridge is moving in the right direction. I will now plot the resultant displacement. We can clearly see the new maximum deflection value of 1.27 millimeters. In other words, we were able to reduce the resultant deflection roughly by 30% by increasing the section modulus of the cross-section. This is an example of a quick first-pass analysis to check deflection. Please keep in mind that we also have to check the stresses to make a well-informed design decision. In real-life bridge design scenarios, structural engineers undertake due diligence by investigating all possible failure modes and follow different safety standards and codes. Other failure modes to study may include seismic loads, dynamic loads, resonance, stress calculations, buckling, effective wind, and snow loads. Thank you for watching, and I hope you enjoyed, and I hope to see you all in another interesting STEM topic video.